Welcome. In this session, we'll formulate a simple neural network. This will have a single output neuron, and it will have one hidden layer of uniform artificial neurons. Let's make a note of what this will look like. We'll have a neuron, and this will be, let's represent its output as the value z, and that value has a subscript of 1. And then let's suppose for now that we only have two hidden neurons. So we'll represent this as this. It will be layer 2, and that will be number 1. This will be layer 2, and that will be number 2. And then we'll have a single data 1 form, and this is the input to layer 2, so that will go to both of these. And then this, and then we'll have to append a 1 onto it. So let's just observe that that will go over here and here. And then this will go in this, the hidden layer outputs will be the inputs to layer number 1, and this will also have to have a 1 appended to it. We'll keep that in mind as we're going. So now let's write down some of the mathematics we need. Originally we said that the summation for a neuron depended on the weight vector, and now we're saying the summation for the output layer depends on its weight vector, and that will be the data coming into layer 1 times the weight vector for layer 1. Over here, the data coming into layer 1 is this and this and this catenated together to make a 1 form. We'll need to differentiate this. So the derivative of the summation for layer 1 with respect to the weight vector for layer 1 will be the data coming into layer 1. We'll also have a nonlinearity, which is how we're computing this z value. So the derivative of the activation function for layer 1 with respect to its linear summation is we're going to represent that as some function phi. And now we can put this together and we can say that the derivative of the activation function for layer 1 with respect to the summation for layer 1 is the derivative of the activation function with respect to the summation, oh, that's supposed to be a w, is times the derivative of the summation with respect to that weight vector, and that will be the activation function's derivative for layer 1 that is a function of the weight vector of layer 1 times the data that are coming into layer 1. So we'll derive only a simple case. So let's declare that now. Simple case only have one form going into layer 2. So now we'll be using these subscripts. So now the layer 2 terms, what do those look like? Well, that would be, so for if we're having only 2 neurons, so let's say 2, we'll put that in quotes for the first time, 2 hidden neurons, and we'll say they have the same activation function, and so the linear products are, so these weighted sums this will be a weighted sum, and it's in layer 2, and this will be I is 1, I is 2, and that will be that data coming in. So let's drop that leading subscript for now, and times the layer 2 weight vector for hidden neuron I. So over here we'll have this data coming in, and that will go to number 1 and number 2, and so we'll have 2 of these weighted sums. Eventually we have to gather things together, so let's do that gathering now. So let's gather weights, and what we'll do is we'll say a weight matrix for layer 2 is, and we'll create this as the weight vector layer 2 neuron 1 and followed by weight vector layer 2 neuron 2. And this is similar to what we did when we started to look at the Kronecker product. So now we can gather the linear products. And what we can do then is we can say that these linear products, which will be a 1 form, that are a function of the weights for layer 2, we'll define these as the product of the data coming in with this. So what we can see is that if we multiply the data by this weight matrix, the first computation will be the 1 form times weight vector 1, and that'll give us U21. Then we'll take the data 1 form times the weight vector 2, and that will give us U22. So all of this is working out quite well. Now we'll have to activate them. So the activations, which are the nonlinearities for the neurons, are, let's call this the results for layer 2 neuron number I. These are a function of this weight matrix, and that will simply be the same function. We'll always use this same activation function, and this will be operating on this term. So that'll be U2I, which is itself a function of the weight matrix for the hidden layer. So now we can gather these, and we can say that if we take these, each one of these is an observation, and so observations go as rows, and so that will be a 1 form. So we can gather these as the Z1 form for layer 2, which is a function of all of the weights, and we will define that as the activation function operating on the first linear sum. So that will be that activation operating on the first linear sum, followed by the activation for the second linear sum in layer 2. And you can imagine that if we had more neurons in this hidden layer, this weight matrix would simply become, it would always have the same number of rows, because that's one more than the size of the data that are coming in, and then the number of columns would correspond to the number of neurons that we have in that layer. And then when we activate those, then this computation, the linear sum, will likewise grow, and so there will be one entry for each one of the neurons in the hidden layer, and then when we activate them, similarly, we're going to have one of these for each one of the neurons. But For these sessions, we'll stick with just having two neurons in our hidden layer.